All right, this is 2000, year 2000, question 6. We have a random sample of 400 married couples was selected from a large population of married couples. Heights of married men are approximately normally distributed. Well, that's important, with a mean of 70 and a standard deviation of 3. And as usual, I like to draw a picture, and I'm going to draw it down, not where I need it, but nonetheless, I'm going to draw it just to remind you guys that when they give us something like that, we probably should be drawing it. Even if we don't need it right away, we probably will need it at some point. So we have mean of 70, standard deviation equal to 3. And this is for the men. Heights of married women are approximately normally distributed with a mean of 65 inches and a standard deviation of 2.5. So once again, here's our mean of 65. This is for the women. And we have a standard deviation of 2.5. So when we look at this, we go, hey, the men are taller than the women, but there's less variation in the heights of women than there are of men. There are 20 couples in which the wife is taller than her husband. Now, that's interesting. So 20 out of 400, there are 400 that we sampled, and 20 out of 400, the wife was taller than her husband. And there are 380 in which the wife was shorter. And part A says find a 95% confidence interval for the proportion, which is nice of them to tell us the proportion of married couples in the population for which the wife is taller. Well, how often was the wife taller? 20 times out of 400. So that's probably the information we're going to use. And it says interpret your interval in the context of this question. Even if they don't tell you to interpret it, you always have to do so. Okay, so this was really nice of them. This is a question 6, and essentially they started you off with running basically a basic confidence interval without a whole lot of tricks to it. So it says the very first thing we need to do is define our parameter. So let P equal the true population proportion of married couples in which the wife is taller than her husband. And our formula for the confidence interval is going to be P hat plus or minus Z star P hat Q hat over N, where N is our sample, and Q hat is just 1 minus P hat. Now we need to figure out what P hat is. Well, P hat is X over N. So that's the 20 times that the wife was taller than the men out of 400. So P hat equals 0.05. So we kind of know everything we're working with, but we need to make sure that we've met our conditions. And the very first condition is random sample. And if I look, they told us it was a random sample, and that's given. So we're good to go there. The next thing, we go to our Goldilocks. Not too big, but big enough. So we need to know N is less than 10% of the population. So in this case, we have 400 samples, 400 couples divided by 0.1. And we basically know that there are more than 4,000 married couples. And they also told us that it was a large population. But since they didn't tell us what the population is, I'm going to assume that there's more than 4,000, because there's definitely more than that in the US or the world, wherever you want to choose. NP has to be greater than 10. And normally we would use a P hat. All right. And we basically go, in this case, it would have been 400 times 0.05. However, we didn't have to do the multiplication part. Wasn't necessary. Why? They told us how many were greater. They told us we had 20, 20 was greater than 10. So we have enough to qualify there. And then the 400 minus the 20 is 380. And that's also greater than or equal to 10. So once you've done that, that's not enough to just by itself. You need to make sure that you go back and say, why was that important? It's large enough to use the normal approximation. This is a special word. Make sure you're using approximation, or you're saying it large enough to be approximately normal. but make sure you're saying approximate or reasonable or somewhat, okay? Though it's not normal, it's approximately normal. So now we have our equation and we've checked our conditions. And we know that p hat is basically the 20 over 400 or 0.05, so we can plug that in. So we have 0.05 plus or minus, I'll come back to the z star in just a moment. The square root of 0.05 times 0.95 divided by our sample size of 400. So the z star, just as a reminder, to do that, we're going to go second vars, inverse norm, and our area is our confidence level, so parenthesis 1 minus 0.95 close parenthesis divided by 2. Oops. I ended up in the wrong spot somehow. Parenthesis 1 minus 0.95 close parenthesis divided by 2. Mean is 0. Standard deviation of 1. And so mean is 0 and a standard deviation of 1 because we're working with the z-score. And we're always just going to choose a positive value. So we end up getting 1.96. And one thing I should talk about real quickly, anytime you're working with proportions, it's a z. All right. So anytime you're working with proportions, it's a z star. Okay. So if they're asking for a confidence interval and you're working with proportions, it's going to be a z. So now that I've plugged in all my information, and this is my work shown. All right. Now that I've done that, I'm going to go ahead and run this thing. I'm going to go stat, test, scroll way down to one proportion z interval, which happens to be letter A. The number of couples that are where the wife is taller was 20. The sample size is 400. And I have a confidence level of 0.95. So I end up getting, this is my lower bound and this is my upper bound. And what that really is saying here is we expect the true population or proportion of where women are taller than the men in a married couple is in about 2.8% to 7.1%. And our best estimate, and by the way, this is not what they asked, but our best estimate is always p hat, which is the midpoint. So our best estimate is that 5% of women, of married women, are taller than their spouses. But we are 95% confident that the true population proportion lies within this interval. So the next thing is we're going to state that. We are 95% confident that the true population proportion of married couples in which the wife is taller than the husband lies within the interval 0.028 to 0.071. And I'm going to pause at this point, if I can find my arrow. There we go. So part B, suppose that a married man is selected at random and a married woman is selected at random. Find the approximate probability that the woman will be taller than the man. So basically, they're not looking at a married man and his wife or a married woman and her husband. They're just randomly selecting from the group of married men and randomly selecting a woman from the group of married women and go, hey, who's likely to be taller? Okay. Well, and they said find the probability that the man will be taller than the woman. At this point, we have two different means. We have a mean of 70 and a mean of 65. And we're looking for a difference because we want to know what the expected difference is. And basically, I'm just going to subtract. And the nice thing is we can directly subtract means. So 70 minus 65 gives me 5. So in general, we expect the man to be 5 inches taller than the woman. All right. Well, that's nice and well and good, but we can't do that with standard deviations. We can't just add standard deviations or subtract them. Matter of fact, we never subtract them. So in this case, the standard deviation for men was 3 and the standard deviation for women was 2.5. Remembering when we can't subtract them, we can only add them, we have to sum them. But before we can even sum them, we have to convert them to a variance. And so when we combine them, we find out that we have 3 squared plus 2.5 squared, take the root of that, and we find out that the variance for the difference between men and women is 3.9051. Now, here's what we have. We now have a new normal curve. And our new normal curve has a mean of 5 and a standard deviation of 3.9051. That's our new normal curve. And obviously this number line continues this way. And it'll go all the way up to positive infinity, and it'll go all the way down to negative infinity. But what I'm interested is where the man is, where the woman is taller than the man. Well, this is going to go 5, 6, 7, 8, ... This is going to get smaller as I go this way, 4, 3, 2, 1. So it becomes, the woman becomes taller in this area right here, where the difference is a negative number. So this is where the woman becomes taller, in this shaded area. So what all I'm having to do is set up a z. The probability that z is less than 0, or this difference is less than 0, is that. So I'm just going to run a normal CDF, second vars, normal CDF. If I were looking at my drawing, this is going off to negative infinity and stopping at 0. So negative infinity, upper bound 0, mean is now 5, and our standard deviation is 3.9051, which again was the square root of 3 squared plus 2.5 squared. When I do that, I end up getting 0.1002, or about 10%. So if I randomly select a married woman from the population and I randomly select a married man in the population, about 10% of the time, the woman will be taller than the man. Now, one thing I want to caution you before I go any farther, because I need to get this out. I can only combine standard deviations if, in fact, they are independent. All right. But since I'm randomly selecting a man and randomly selecting a woman, it's reasonable to assume that their heights are going to be independent, that the man's height and the woman's height are not dependent upon each other, randomly selected from the population. But remember, in order to sum standard deviations, they must be independent. That's not true for means. We can do means anytime we want to, but for standard deviations, they must be independent. So based on your answers to A and B, are the heights of wives and their husbands independent? Explain your reasoning. And I'm like, well, what were my answers? Well, my answer here was 10%, and my answer here was a confidence interval. So those are my answers. And what I was expecting to find from the confidence interval is that the difference between married couples lies here. And I look at that 10%, and that doesn't lie within that interval. It's above that interval. It's somewhere up here, above it on the positive side. So because it doesn't lie in the interval, it doesn't appear to be independent. Because this is what we expect to happen if we randomly select married people, but here's what we find out happened when we have the couples. So the heights of married spouses appear to be related and are not independent. Now, I made a comment. I have to back it up. We demonstrated that 10% of married women are taller than married men. We did that in part B. However, the 95% confidence interval estimated the true population of married couples in which the wife was taller only occurred between 3% and 7% of the time. The interval does not contain 10%. If couples' heights are truly independent, the 10% value would have been contained in that interval, or the interval would have been wider, one of the two. So here we go. And it starts off, a scatter plot not shown of husband's height versus wife height for the 400 couples in the sample shows an approximately linear relationship with a correlation of 0.4. And I'm like, well, if the correlation is 0.4, that's not a strong correlation. That's kind of a weak correlation, but there is a correlation, but it's not very strong. On the graph below, sketch in an ellipse. Wait a second, you want me to sketch an ellipse of a scatter plot that's not shown? That could enclose the points of the scatter plot. And I'm like, are you crazy? How's that going to happen? And I really have to think. So, and then it says, be sure to label your axis and locate and orient your ellipse correctly with respect to the two axes and the lines y equals x. And I'll be truly honest with you. The first time I ever read this question, I was like, I don't have much idea. Let me go back and read what they told me at the very beginning. And that's what I did, is I went back and read what they told me at the beginning. They said, oh, married men have a mean of 70 with a standard deviation of 3. And I go, oh, let me think for a moment. I can use the empirical rule, and plus 3 standard deviations means up 70 to 79, down 3 standard deviation is 61. And I know that 99% of the men, or 99.7% of the men, lie in the interval 61 to 79 inches. I'm not sure if that's going to help me out, but that's what I was thinking. I was like, I'm going to sketch that here on my graph in a second. And then I had the married women, and 2 and 3 standard deviations above would be 72.5, and 3 standard deviations below is 57.5. And I was like, well, I'm going to start with that, and I'm going to label one part of the graph men and one part of the graph women. As it turns out, it doesn't matter which axis you labeled the women and which axis you labeled the men. So I said, well, 61 to 79, and then I drew 2 vertical lines straight up. Then I went to the women's and I went, well, 57.5. And I go, well, 70's here. So that's close to 72.5. Obviously, we're just guessing. Okay. And really, I should be labeling these, and you should see that I did below. And so I ended up with this intersection right here. And I was like, oh, that's where my ellipse needs to go. And so I just kind of sketched out an ellipse in pencil right here. And this part right here, this little bitty small part, or the small part, is where the wife is taller than the husband. All right, that's where the wife is taller than the husband. So the women's height, 57.5, because it's 65 minus 3 standard deviations, and then 65 plus 3 standard deviations. And that gave me these levels right here. This is at 57.5. And this is at 72.5. And then 70 minus 9, this is 61. And this is 79. And then I just fit my graph, fit my ellipse as best I could there. Now, one thing I want to say about problems like this, start with what you know. It's okay to struggle. I've been to many AP trainings and the teachers struggle. The fact of the matter is, almost every year I see a question 6, I have to read it 2 or 3 times myself before I know where to go on some parts of it. And some of them, like this one, I just started working the problem and then it actually came together for me, but I really didn't know going into it. All right. We're good.
All right, so there were 4 sections of this question, and each section is graded separately. So for part A, this part A, because it was a little bit straightforward, so we're hoping that this is one of the times where you get the full E on this section. Some things that there's some special notes I want you guys to understand is that when we talk about our conditions, you can't just state them and they phrase it as not same as checking for the assumptions, right? So you can't just say it's large enough and things like that. You have to show the work for each of those conditions. So they made a note that as long as you had the right formula, you did all the conditions, you did the correct computations, and you gave the correct interpretation in context. And Mr. Spencer talked about that. Even if they don't ask it, we're always giving the interpretation in context. It's always going to be part of that grading rubric. So if you did all of those parts, you got your full E. If you missed one of the 4 parts, that could get you partially correct for part A. Then for part B, where you had to calculate the combined mu and standard deviation, and then calculate a probability. They looked at them as 2 separate things. So if you got both calculation of the random variables together and the correct probability, of course you got an E. But say you messed up on, it's more likely that you messed up on combining the standard deviations, right? So say you did that part incorrect, but you did the right calculation work for, based on your wrong number up here, you used it to calculate the probability, you could still get a partial credit, and vice versa, even if, and flipped the other way. So you did this correct, but you couldn't do this part correct, finding the probability, then you could still get a partial. So hopefully you get at least a P for part B. Then for part C, where you're talking about independence, they made a very strong note that you had to refer back to the interval, that your justification about independence or dependence in this case had to be on the fact that our probability that we calculated was not within the interval. If for some reason you got a different number in part B, but the judgment that you make follows correct logic, you can still get part C essentially correct, as long as you didn't make a logic mistake here. If you did not use that interval, they consider that as a weak argument and you don't get credit. So you do have to use the work that you got from part A and B to make a judgment about independence or dependence, depending on what your work looked like. So even if you got part B incorrect somehow, right, you could still get part C completely correct as long as your logic followed. So we're hoping that's another place where you got another partial credit. Now for part D, as weird as the topic, the task they had you do, they broke down the ellipse into parts that are, I think, somewhat achievable, right? They were looking for 5 major components on that graph. The center of the ellipse, I think, is something that maybe some of you guys would have naturally gone to, because these are the centers, these are the means for the men and the women. You would have labeled your axes because we tell you to do that all the time. And then you probably would have had your orientation on the ellipse as a positive slope. So I think that those 3 things you guys, I feel pretty good that you guys could have done those things, even though you wouldn't, maybe some of you guys weren't sure how wide to draw the ellipse or the oval. You would have got at those 3 parts right, and getting 3 actually is partial credit for task D. So that was something that I think is achievable. Like a lot of us are going to be on that track where we're naturally doing the axes, so we're going to get that. The small overlap might have been another one that some of us got because there wasn't a lot of women that were taller than men. So if you made that connection, that might have been something else that you picked up for that. This is one of those problems where they're looking at it holistically. They don't really have half points. So they're grading it like this, but for every partial that you get, they're looking at holistically to see if it bumps you up. So some partials may bump if you're, when we look at it and you have 3 E's, but you have some partials, you might be bumped up to a 4 depending on what those partials look like. So this is one of those that they're looking at you holistically. So trying to get all the P's that you can along the way could bump your entire score up for this problem. Any questions on the grading part, how they would have scored you?
I'm just going to add one last comment that please remember, question 6 is, we're not expecting perfection. If you're shooting for a 5, 2 points, if you get 2 points, you're well on your way there. I mean, so there's 4, they're worth 4 points each. And so if you get two out of the 4, you're well on your way to a 5. And we feel really good about your chance of making a 5 if that happens. So that partial points that she's talking about, super important. Be encouraged, don't be discouraged. Do what you can on those and get what you can out of them.